Today we're going to be talking about polynomial regression, which allows us to model curved relationships between variables. So with other types of regression, we've been modeling a straight line where we think one variable is in a linear relationship with another variable. So quite often we'll see relationships which are not linear in nature. We'll see things that are curved in nature. And let me give you a few examples of relationships that are not straight line relationships. So one example is the idea of fear as a motivator. So we see many advertisements and many types of political ads where fear is a motivator, and it gets us either to vote against a candidate or it gets us to change some health-related behavior. So if we plot this data, we find that it's not a straight line relationship. So here's a plot of the data where we have fear as our x variable or predictor variable and motivation as our outcome variable or y variable. So as fear increases, we see motivation also increasing at the beginning of this relationship. So more motivation at the beginning. Imagine, for example, on cigarettes, you see sometimes advertisements saying, or not necessarily advertisement messages saying that smoking might cause lung cancer, smoking increases risk of pregnancy complications, and maybe that motivates people to either stop smoking or at least to think about stop smoking. But as the fear message becomes more and more severe, we see the relationship changing, and it actually, at some point, it causes people to become less motivated. So, for example, in some countries, they put very explicit pictures on cigarette packs which show people's lungs after they've died from lung cancer, lungs full of tar, etc. And this can actually cause people to shut down or to become less motivated. We don't need to speculate on what the cause of this relationship is, but it actually causes... Another famous example of a non-straight line relationship is the Yerkes-Dodson law, and this is as people become more aroused or more anxious, they have declines. So let me show you this in a graphical format. We can see that if you're really not aroused or you have no anxiety, you're almost asleep, your performance will be very sleepy or lackadaisical. If you have a little bit of anxiety, it motivates you to do better. So when you have a little bit of anxiety, your performance goes up. If you have too much anxiety or too much arousal, a person can no longer function anymore. So then performance is going down. So here's another example of a non-straight line relationship between variables. A final relationship is change across treatment. So this is a clinical study where we see people's symptoms go down across treatment. However, it's not a straight line relationship as it goes. If we see people start off with a high amount of symptoms, at the beginning of treatment, their symptoms go down quite quickly. They're getting a lot of gain right from the beginning. As they continue through treatment, they're still going down, but not as quickly as when they started. So the reduction in symptoms is still occurring, but not as quickly. And then when they end treatment and they're not doing any sort of treatment, we catch up with them maybe 6 months later, we might see some increase in symptoms, but it certainly hasn't gone back to where they started. So this relationship is not a straight line relationship. In order to model these non-straight line relationships, we're going to need some extra tools to model this. So there are many ways we can model these non-straight line relationships. So one we're going to be talking about today is called a polynomial regression model. And it's very similar to what we've been using already with a linear regression model. And if you look at this equation, the very beginning part is exactly the same as what we've seen. So we have a y variable being predicted by an intercept. So that's our correction factor. That's where people begin when they have 0 amount of x, plus a slope times our x variable. So this is either, if it's a positive slope, people are increasing. As people increase in x, people increase in y. If it's negative, as people increase in x, people decrease in y. So that's our slope factor, and then here's our x variable. So each person has a certain amount of x, which will go to y. So that part of the equation is exactly the same. At the very end of the equation, we have our error term. No prediction is perfect, so we'll always have some error involved in our equation. What's new in this equation is the second part here, our second slope variable. Our second slope regression coefficient is multiplied by x squared. We're just squaring that x. This is the same x variable we have here, but now we're squaring it. So what this allows us to do is to model non-straight line relationships. So this allows a curve in our relationship. And I'll show you this in a picture in just a second, but it allows for one curve. We can also do a cubic model. Cubic model is exactly the same as what we just saw, except now we're going to cube the x variable. And when we cube it, we actually can get a line with 3 bends. So when we have a square relationship, we get 1 bend. If we cube it, we can get a second bend. Oops, that's actually a 4th bend. If we were to raise it to the 4th power, we could get a 4th bend as well. So there's a simple relationship between how many polynomial terms we have, and basically you subtract 1 from the highest order, and that's how many bends you get. So if you square a variable, you would actually get 1 bend. So you raise it to the 2nd power, so 2 minus 1 gives us 1 bend. Cube, this is actually the square. If you square it, you subtract 1 and you get 1 bend. If you cube it, you have to the 3rd power minus 1, you'll get 2 bends. And that's not very good handwriting, but basically you get 2 bends when you have a cubic model. You could put as many polynomials in as you want. You could have it raised to the 4th power, 5th power, etc. But usually we don't see relationships that have that many bends. So we in social sciences, we'll see maybe 3 bends at most, but so we're not seeing too many higher order polynomials in our equation. So let's look at an example. This comes from another textbook by Jacob Cohen and Patricia Cohen, West and Aiken, and what they're looking at is the number of credits undergrads take in their minor, and how much interest they have in that and further study in that area. So for example, if you're taking a minor in psychology and you take more credits, maybe you have more interest in pursuing a psychology degree in graduate school. So let's look at the data, and we have the first column is just an ID variable. This is just the person's ID. Second column is how many credits they have in that minor. Many different people here with varied amounts of credits in the minor. And then we have an interest variable. And this interest variable, the higher the amount of interest, the higher that this variable will show. So this person here with 21 has much higher interest in pursuing a graduate degree than this person with a 13. So one of the best ways to look at our relationship is to plot it with a scatter plot. So if we look here, we have the number of credits people take in their undergraduate minor, and starting at 0 and going up to 20, and then we have the amount of interest they have. So this person here took a low amount of credits, looking around 3, and has an interest somewhere right around 4. So not much interest, but not many credits. So if we try to fit a line to this data, if we fit a straight line, let's see if I can actually draw this. It would look something like this, and it does fit the data pretty well. However, maybe a curved line might fit the data a little bit better. So what I mean by fitting the data, we see less distance between the line and the points. So that's what we're aiming for all the time, is trying to find the best fit for the data where our line matches up the data as much as possible. And our square value is what really tells us how well our line is at predicting our data. So what we're going to do is we're going to fit a series of models, and we're going to try to figure out which model fits our data better. So as I just mentioned, our R-square value is really what's going to tell us how good of a predictor we have. So we're going to look for the highest R-square value, and we're going to want to make sure that whenever we add another predictor or another band to our model, that the R-square change from the previous model is a significant amount of change, that we're adding more prediction to our model. I'll explain that more as we go through the results and talk a little bit more about the data. So if we look here at, this is the first model that we're going to try to fit, and this is a straight line model. So what we have here is a predictor of number of credits, and our dependent variable is how much interest we have. But I don't have all of the data in this output. There's some, I'm sorry, not all of the tables are in this output, but we have the most important ones. So we can see here the relationship between the two variables. It's a very high correlation, R.749. Really strong relationship between the two variables. Our R-square, which is simply the R value squared, which tells us how good a predictor we have, is 0.561. To put that another way, we're explaining 56% of the variability in interest by the number of credits. So R-square, again, is how much we explain in Y given our X variables. That's a really good number. We don't often see that in social sciences type study, this data. So it may be a little bit better than we expect to see. Our square value, we're explaining a lot. We can explain even more by adding a curve to the data. What this is basically telling us, this is a simple regression. We're fitting a straight line data, and we can actually come up with a regression coefficient. Basically, our constant is 18, so we start off at an interest level of 18, and for each credit will go up, they go up 1.15 units of interest. So we have a straight line function. We see that the slope is positive, so we're going in a positive direction, meaning the more credits you take, the more interest. So here's our straight line fitting to the data, and if you look, it doesn't fit very well down here, and maybe a little up here, but we're kind of getting, we can kind of see maybe there's a curve relationship to this data. So let's see if we can do a little bit better. We'll fit a model where we allow one more polynomial variable in there, and we'll see if we can better. So here, let's try a quadratic component. So what we're going to try to fit is just write up the simple equation, y equals a constant a, that's an a, plus our first slope, our linear relationship, plus our x variable squared. And what this allows our curve to do is to have a bend in it. So it can bend like this. It can also bend the opposite direction. It can do many different things. So this is what we're going to try to predict with our next model, our results. So in this output, we have two models. The first model is a straight line relationship. The second model is our relationship with the curve. And the way we do this is doing the sequential or hierarchical regression, where we put in the first block, we put in component, and the second block, we put in our polynomial. So that's how we get two different models. So we see in the first model, the same exact output that we had before. In the second model, we see our R square, and now allowing the line to curve by putting in that square term, our R square goes up to 0.67. So that's increases the exact amount of increase, 0.112. So we see an R squared change of 0.112, so explaining 11.2% more variance in interest by adding this squared term. And we can see that this is a significant amount of change, meaning we're explaining a significant amount more variation in interest. So what we're looking at, we want to see an increase in our R square. We also want to make sure it's a significant increase. Usually whenever we add variables, the really silly variables, see some sort of increase. So it's not just seeing some sort of increase, it's seeing a significant amount of increase. So we really want this number to be significant, or we say this model is better. And then when we look down below, we see our how we compute our regression line. We see the constant variable, the linear variable, and then our polynomial variable. So we see there's some things to interpret here. 1.206 is positive, meaning in general, we're going to have some curve that's going up the whole time. This is negative, meaning that our curve is going to have an upward bend. So it starts off fast and then slows down as we go. So that negative tells us what our curve is going to look like. If it were positive, we'd start off slower and then get quicker as we go. So this negative tells us that our curve is going to bend like this. And you can see that all of these, the linear term and the polynomial term, are both significant. So here is our data plotted out with those two curves to it. The straight line curve in green, and the gray is our polynomial term. The gray actually fits the data better. We just saw with our square went up 11%. So this curve line really fits the data a lot better, and then we'll want to use that to tell the relationship between the two variables. It's not just a straight line relationship. It seems that as students take more credit, eventually their interest starts to decrease. So maybe at some point in time, they just get maybe sick of the minor and just don't want to have anything to do with it anymore. Of course, it's speculation, but something's happening in this relationship where it increases at first, but then it starts to slow down as they take more credit and they don't want to continue on after that. So just as a final point, this is just sort of a bonus. You can actually figure out where that point is, the sort of point where people start losing interest. And this might be important. And this example we had is not a, maybe a groundbreaking study of looking at interest and if they want to go on to graduate school, but maybe college administrators might want to know how many credits should students be taking in their minor before they start losing interest. And so what we can do is, if we do a little bit of calculus, we can come up with a formula that gets us where that inflection point is. So if we just take this formula here, that tells us where that point is where they start to lose a little bit of value, where it is they're increasing, but then that point here is where it starts to inflect and they start to, you don't get as much value. For each extra class you've taken, you're still gaining interest, but at some point you're not getting as much interest as the class before. So that can be important. And you can imagine in economic models or in other models that you have more interest in, where this is going to be really important. You want to find out where do you start losing that benefit, or if it's a sort of a curve goes the opposite direction, where do you really start to gain that benefit? How much of something do you have to have before you start to gain more benefit? So this can be important for some people, but again, this is just a sort of bonus little formula. So in general, when we're talking about polynomial regression, we're looking at fitting our data with non-straight line relationships. This is one tool we can have where we want to fit things that aren't straight line, and many relationships in the real world are not straight line relationships. So thank you very much.